Welcome to my presentation. The title of this work is Digital Feedback Design for Mutual Coupling Compensation in Gradient Array System. We received research grant from Aselsan. Gradient array systems produce highly flexible spatial encoding magnetic fields. In these systems, multiple gradient coils are driven individually by independent gradient power amplifiers. Our motivation is accuracy of gradient current waveform decreases due to mutual coupling between coils. Conventional systems use feedback for current compensation. However, in array systems, GPA's limitation might fail to fully compensate the effect of strong mutual coupling. First-order feed-forward model was already proposed to overcome this issue. However, feed-forward is based on the knowledge of system, therefore high-order terms, nonlinear and time-varying parameters, and also measurement errors can affect this method. Here we propose a closed-loop feedback in combination with feed-forward for gradient array systems. This is the block diagram of gradient array systems. The first-order model provides the required voltage in the feed-forward path according to the command input. Here, M is a matrix including self and mutual inductances, and R is a resistant matrix. The PWM signals are generated with 500 kHz switching frequency and 15-bit time resolution. A home-built full-bridge power amplifier is used to provide the required voltage and currents. And finally, the PID controller will update the required voltage by changing the duty cycle of PWMs. Assuming gradient array system as a linear time invariant system, all the system can be shown by 3 transfer function blocks, as you can see in the figure. And the transfer function of whole system will be like this, which here, G of P is the transfer function of gradient coil with amplifier, G of M is the characterized model, and G of C is the controller. Considering 2 channels of array and single input, single output PID, this is the direct transfer function of channel 1, and this is the cross-term transfer function of channel 1. Assuming this term approximately 1, which is true if we can characterize the system properly, by taking the gain of feedback loop much bigger than 1, we can approach to the desired waveforms. This will happen by increasing the gain of controller at the operating frequency. We compared the results of feed-forward only, feedback only, and combination of feed-forward and feedback in simulation for 2 channels. In the simulations, we considered second-order behavior for gradient coil with amplifier and applied 2% error for measurement parameters. To find the PID coefficients, we used the Ziegler-Nichols method. As shown here, feed-forward only cannot compensate for system uncertainty. Also, feedback only fails to correct the rising and falling portions due to mutual coupling. However, feed-forward plus feedback provides a good compensation for the errors. We also did image simulations for different cases. We applied the GRA sequence and used the under test waveforms as a readout gradient. The error between ideal case and feed-forward and also feedback is in the range of 10 to minus 7. However, for feed-forward plus feedback is in the range of 10 to minus 9, which shows a significant improvement. And these are our experiment results, which are in a good agreement with the simulation results. The hardware limitation were the same for all cases. We used a relatively long pulse to see the effect of time-varying parameters. As a conclusion, here we propose the fully digital controller which contains the feed-forward and feedback simultaneously. This method will give 2 degrees of freedom to deal with mutual coupling and unmodeled parameters. Also, it will increase the bandwidth of overall system. As a discussion, if the system can be characterized perfectly, there is no need for feedback. However, in the real cases, the uncertainties and measurement errors, which cannot be modeled, affect the system. Also, feedback is necessary to reject the external disturbances. Feedback only fails to fully compensate the effect of strong mutual coupling due to hardware limitation. Using an ideal gradient amplifier with infinite voltage might be a solution for it. As a future work, better characterization of system will improve the performance of feed-forward and will decrease the load of feedback loop. Thank you for your listening.